All right, in this lecture, we'll begin our discussions on Poisson point processes. Let's begin by considering the d-dimensional Euclidean space denoted as R to the power d, the collection of Borel measurable subsets of this Euclidean space, which we'll write as script b of R to the power d, is generated by sets of the form b of x. B of x is defined as the set of all points y in R to the power d such that each component y sub e is less than or equal to the corresponding component x sub I for any given x in R to the power d. Now let's define a simple point process. A simple point process is a random countable collection of distinct points. We can represent this as S mapping from our sample space omega to script x raised to the power of n, where script x is our underlying space. A key characteristic is that the distance or norm of Sn, the nth point, tends to infinity as n approaches infinity. Just a reminder here, because S is a simple point process, every point Sn is unique. This uniqueness allows us to think of S as a random set of points within the space script x. Consequently, S intersect A represents the random set of points that fall within a given set A. As a further reminder, for any simple point process S, the probability of the event that Sn equals Sm for any n not equal to m is 0. Also, the number of points in S that intersect with any bounded set A, an element of script B of script x, denoted as the cardinality of S intersect A, is finite almost surely. Let's consider an example to make this more concrete. Say a simple point process on the half line. We can simplify our general definition when d equals 1, when our space script x is the set of non-negative real numbers r plus. We can order the points of the process S, which maps from omega to r plus raised to n. This gives us an ordered process. Let's call it S tilde, also mapping from omega to r plus raised to n, such that S tilde sub n is S sub n, representing the nth order statistic of S. That is, we define S not to be 0. And S sub n is the infimum of the set of all Sk greater than S sub n minus 1 for k in the natural numbers. This ensures that S sub 1 is less than S sub 2 and so on up to S sub n and beyond. Also, the limit as n approaches infinity of S sub n is infinity. We will often refer to such an ordered process as an arrival process. Corresponding to a point process S, which maps from omega to script x raised to n, we denote the number of points that fall into a set A, an element of script B of script x by n of A. This is defined as the cardinality of S intersect A, which can be written as the sum over n in natural numbers of the indicator function of A applied to Sn. It's clear that n of the empty set is 0. The resulting process n, which maps from omega to z plus non-negative integers raised to the power script b of script x, is called a counting process for the point process S. A quick reminder on a property of counting processes. Let A be a collection of k sets A1 through AK, which are elements of script B of script X, and form a bounded partition of some set B also in script B of script X. Due to the disjointness of A1 through AK, we have n of B equals the sum over n in natural numbers of the indicator that Sn is in the union from I equals 1 to k of AI. This can be rewritten as the sum over n in n of the sum from I equals 1 to k of the indicator that Sn is in AI. Swapping the summations, this becomes the sum from I equals 1 to k of the sum over n in n of the indicator that Sn is in AI, which is simply the sum from I equals 1 to k of n of AI. Now a definition, a counting process is called simple if the underlying point process that generates it is simple. As a reminder, for a simple counting process n, we have that n of the set containing a single point xn of set x is less than or equal to 1 almost surely for all x in script x. This just means we don't have multiple points at the exact same location. Another reminder, let n mapping from omega to z plus raised to script b of script x be the counting process for the point process s, which maps from omega to script x raised to n. First, it's important to note that the point process s and its corresponding counting process n essentially carry the same information. Second, the distribution of the point process S is completely characterized by the finite dimensional distributions of random vectors of the form n of A1, n of A2, dot, n of AK for any choice of bounded sets A1 through AK in script B of script X and any finite k in the natural numbers. Let's revisit our example of a simple point process on the half line. Since the Borel measurable sets script B of R plus are generated by half open intervals of the form half open set 0, T for T in R plus, we denote the counting process by n mapping from omega to z plus raised to r plus. Here, n sub t is defined as n of the half open set 0 t, which is the sum over n in natural numbers of the indicator function that Sn is in the half open set 0 t. This n sub t counts the number of points in the half open set 0 t. For any s less than t, the number of points in the half open set s t is given by n of half open set s t, which equals n of half open set 0 t minus n of half open set 0 s, or simply n sub t minus n sub s. There's an important theorem by Renyi. It states that the distribution of a simple point process S mapping from omega to script x raised to n on a locally compact second countable space script x is completely determined by what are called void probabilities. These are the probabilities of the form probability P that n of A equals 0 for all A in script B of script X. Let's sketch the proof of Renyi's theorem. It suffices to show that the finite dimensional distributions of S on locally compact sets are characterized by these void probabilities. We'll proceed in steps. Step 1, we will show this by induction on the number of points k in a bounded set A, which is an element of script B. Let A 1 through AK and another set B all be locally compact sets in script B of script X. We want to show that UK, defined as the probability of the intersection of events n of I is greater than 0 for I from 1 to k and n of B equals 0, can be computed from void probabilities. For the base case k equals 1, we have the probability that n of A1 is greater than 0 and n of B equals 0. This can be written as the probability that n of B equals 0 minus the probability that n of B union A1 equals 0. Both terms here are void probabilities. The induction can then be proved using the recursive relation UK equals the probability of the intersection from I equals 1 to k minus 1 of n of A I greater than 0 intersected with n of B equals 0 minus the probability of the intersection from I equals 1 to k minus 1 of n of A I greater than 0 intersected with n of AK union B equals 0.
Step 2. For any locally compact set B in script B of script X, we can find a sequence of nested partitions. Let's call the nth partition Bn, which consists of sets B and J for J from 1 to Jn. This sequence of partitions is chosen such that as n goes to infinity, it eventually separates all the individual points in S intersect B. We then define Hn of B as the sum from J equals 1 to Jn of the indicator function that n of Bn, J is greater than 0. This Hn of B counts the number of subsets in the partition that contain at least one point from S intersect B. Importantly, Hn of B converges upwards to n of B almost surely as n increases.
Step 3. Next, we need to show that for all locally compact sets B 1 through Bk in script B of script X and for any natural numbers J1 through Jk, the probability of the event Hn of Bi equals Ji for all I from 1 to k simultaneously can be expressed in terms of void probabilities. We observe that the probability of the intersection from I equals 1 to k of Hn of Bi equals Ji can be written as a sum. This sum is over all possible collections of subsets T1 through Tk, where each Ti is a subset of the indices from 1 to Jn, and the cardinality of Ti is Ji. The term being summed is the probability of a complex event for each I from 1 to k and for each j in Ti, n of B superscript Inj is greater than 0 and n of the union of all B superscript Inj where j is not in the union of T1 through Tk is equal to 0. This, by our result from step 1, can indeed be expressed in terms of void probabilities. Step 4. For a simple point process, we have the following almost sure limit. The limit as n goes to infinity of the intersection from I equals 1 to k of the event Hn of Bi equals Ji is equal to the intersection from I equals 1 to k of the event n of Bi equals Ji. The final result then follows from the continuity of probability. As a reminder, the notation absolute value of A, which is the integral over x in A of dx, represents the volume of the set A in script B of R to the D. Now let's define the intensity measure. The intensity measure lambda, which maps from script B of script x to the non-negative reals R plus, is defined for each bounded set A in script x. It's given by its scaled volume in terms of an intensity density function lambda, which maps from R to the D to R plus. Specifically, lambda of A is the integral over x in A of lambda of x dx. If this intensity density lambda of x is a constant, say lambda, for all x in R to the D, then lambda of A simplifies to lambda times the volume of A. In particular, if A1 through AK form a partition of a set B, then lambda of B equals the sum from I equals 1 to K of lambda of AI. Now we are ready to discuss the Poisson point process. First, a definition of a Poisson random variable, a non-negative integer valued random variable n, mapping from omega to z plus, is called Poisson if for some positive constant lambda, the probability that n equals n is given by e to the power minus lambda times lambda to the power n divided by n factorial. A quick reminder about Poisson random variables. It's easy to check that the expectation of n equals the variance of n, and both are equal to lambda. Furthermore, the moment generating function m sub n of t, which is the expectation of e to the power tn, is e to the power lambda times e to the t minus 1, and this exists for all real numbers t. Here's a corollary that links simple counting processes to Poisson distributions via void probabilities. A simple counting process n mapping from omega to z plus raised to script b of script x has a Poisson marginal distribution with an intensity measure lambda mapping from script b of script x to r plus if and only if its void probabilities are exponential with the same intensity measure lambda. That is, the probability that n of A equals 0 is e to the power minus lambda of A. Let's look at the proof of this corollary. It's quite clear that if the marginal distribution of the counting process n is Poisson with intensity measure lambda, then the void probability, which is the probability that n of A equals 0, is simply e to the power minus lambda of A. This is directly from the Poisson PMF with n equals 0. This shows one direction. Continuing the proof, conversely, let's assume that the void probabilities are exponentially distributed with intensity measure lambda. So the probability that n of A equals 0 is e to the power minus lambda of A. It follows from the linearity of the intensity measure lambda of a union of disjoint sets is the sum of their lambdas, that for any finite collection of bounded and disjoint sets b1 through bk in script b of script x, we have the probability of the intersection from I equals 1 to k of the event n of bi equals 0 is equal to the probability that n of the union from I equals 1 to k of bi equals 0. By our assumption, this is e to the power minus lambda of the union from I equals 1 to k of bi. Since the sets are disjoint, lambda of their union is the sum of their lambdas. So this becomes e to the power minus the sum from I equals 1 to k of lambda of bi. This can be written as the product from I equals 1 to k of e to the power minus lambda of bi, which is precisely the product from I equals 1 to k of the probability that n of bi equals 0. Continuing the proof, this means that the Bernoulli random vector whose components are the indicator that n of bi equals 0 for I from 1 to k consists of independent random variables. This holds for any finite k and any collection of bounded disjoint script b of script x measurable sets b 1 through bk. Next, let's consider a set B in script B of script X and a sequence of partitions Bn of B. Each partition Bn consists of Jn sets Bnj such that lambda of Bnj equals lambda of B divided by Jn for all j from 1 to Jn. It follows that Hn of B, which we defined earlier as the sum from j equals 1 to Jn of the indicator that n of B and j is greater than 0. The sum of Jn independent and identically distributed Bernoulli random variables. The success probability for each of these Bernoulli trials, let's call it Pn, is 1 minus e to the power minus lambda of B over Jn. Therefore, Hn of B follows a binomial distribution with parameters Jn and Pn. Therefore, the probability that Hn of B equals m can be written as e to the power minus lambda of B divided by m factorial times the binomial coefficient Jn choose m times e to the power lambda of B over Jn times Pn, all raised to the power m. This simplifies to e to the power minus lambda of B times Jn factorial divided by Jn minus m factorial times e to the power lambda of B over Jn minus 1, all raised to the power m. Recall that in the proof of Renyi's theorem, Hn of B converges upwards to n of B as n goes to infinity. Also, as n goes to infinity, Jn goes to infinity, and the measure of each individual set B and j goes to 0. Using these facts, the limit as n goes to infinity of the term Jn factorial divided by Jn minus m factorial times e to the power lambda of B over Jn minus 1 raised to the m is equal to lambda of B raised to the m. Taking the limit as n goes to infinity on both sides of the probability equation for Hn of B equals m, we obtain the Poisson probability for n of B equals m. Let's define the complete independence property. A counting process n mapping from omega to z plus raised to script b of script x is said to have the completely independence property if for any collection of a finite number of disjoint and bounded sets a1 through ak in script b of script x, the random vector n of a1 dot 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 n of ak consists of independent components. That is the probability of the intersection from I equals 1 to k of the event n of ai equals ni is equal to the product from I equals 1 to k of the probability that n of ai equals ni. This must hold for any vector n of non-negative integers 1 through nk. Now, we can formally define a Poisson point process. A simple point process S mapping from omega to script x raised to n is called a Poisson point process if its associated counting process n mapping from omega to z plus raised to script b of script x possesses two key properties. First, it has the complete independence property we just defined, and second, its marginal distributions are Poisson. The intensity measure lambda mapping from script b of script x to r plus of a Poisson process S is defined by lambda of A equals the expectation of n of A for all bounded sets A in script B of script X. As a reminder, recall that for any partition A consisting of A1 to A k in script B of script X raised to k of a bounded set B in script B of script X, we have n of B equals the sum from I equals 1 to k of n of AI. Therefore, it follows from the linearity of expectation that lambda of B, which is expectation n of B, equals the sum from I equals 1 to k of expectation n of AI, which in turn equals the sum from I equals 1 to k of lambda of AI. This confirms that lambda defined as the mean of the counts is indeed a valid intensity measure that is additive over disjoint sets. Another reminder, for a Poisson process with intensity measure lambda, it follows directly from the definition that for any finite k in Z plus and any collection of bounded mutually disjoint sets, A1 through AK in script B of script X, the probability of the intersection from I equals 1 to k of the event n of A I equals ni is given by the product from I equals 1 to k of e to the power minus lambda of AI times lambda of AI raised to the ni divided by ni factorial. This holds for any n in Z plus raised to k. Now a specific type, if the intensity measure lambda of a Poisson process S satisfies the condition lambda of A equals a constant lambda times the volume of A for all bounded sets A in script B of script X, then we call S a homogeneous Poisson point process and lambda is referred to as its intensity. Let's discuss some equivalent characterizations of Poisson point processes. We have a theorem on equivalences. The following statements are equivalent for a simple counting process. N mapping from omega to Z plus raised to script B of script X. First, the process N is a Poisson process with a locally finite intensity measure lambda. Locally finite means lambda of A is finite for all bounded A. Second, for each bounded set A in script B of script X, the probability that n of A equals 0 is e to the power minus lambda of A. Third, the intensity measure lambda is bounded for bounded A in script B of script X, and for each such bounded A, the number of points n of A is a Poisson, random variable with parameter lambda of A. Fourth, the process n has the completely independence property and the expectation of n of A. Expectation n of A equals lambda of A for all bounded sets A in script B of script X. Let's outline the proof of these equivalences. We will show the implications in a cycle. 1 implies 2, 2 implies 3, 3 implies 4, and finally 4 implies 1. First, 1 implies 2. This follows directly from the definition of a Poisson point process, which includes Poisson marginals, and the definition of a Poisson random variable setting the count to 0. Second, 2 implies 3. We use our earlier corollary. We know from it that if the void probabilities are exponential, then the marginal distributions are Poisson. Continuing the proof, 3 implies 4. We need to show two things here. First, the mean property. Since the distribution of the random variable n of A is given as Poisson with parameter lambda of A from statement 3, its mean expectation n of A is indeed lambda of A. Second, the complete independence property CIP. Consider a partition AA 1 through AK for a bounded set B in script B of script X, then lambda of B equals the sum of lambda of A 1 through lambda of AK. Now consider all possible partitions of a non-negative integer m into k non-negative integers n1 through nk. We can write the probability that n of B equals m as the sum over all such partitions n1 plus dot 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 plus nk equals m of the probability that n of A1 equals n1 dot 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 and n of AK equals nk. Using the definition of the Poisson distribution from statement 3, since n of B is Poisson with parameter lambda of B, we can write the left hand side of this equation as probability that n of B equals m is e to the power minus lambda of B times lambda of B raised to m divided by m factorial. This can be expanded as the product from I equals 1 to k of to the power minus lambda of AI times the sum from I equals 1 to k of lambda of AI raised to m divided by m factorial. Continuing the proof for 3 implies 4. We recall the multinomial expansion a1 plus dot 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 plus ak raised to the power m equals the sum over all n1 plus dot 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 plus nk equals m of the multinomial coefficient m choose n1 dot 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 nk times the product from I equals 1 to k of ai raised to the ni. Using this, we can rewrite. Finally, for the proof of equivalences, 4 implies 1. Statement 4 tells us n has complete independence and expectation n of A equals lambda of A. From corollary 3.1, if the void probability P of n of A equals 0 is exponential with an intensity measure, say lambda prime, then the marginal distribution of n of A is Poisson with that same intensity measure lambda prime. Let's define a function f from script b of script x to minus infinity to 0 as f of a equals the natural logarithm of the probability that n of a equals 0 for all bounded a in script b of script x. Then we observe that for any partition a1 dot 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 ak of a, due to the complete independence property from statement 4, f of the union from I equals 1 to k of ai, which is f of a, equals log of p of n of a equals 0. Since the ai are disjoint and n has CIP p of n of a equals 0 is p of n of a 1 equals 0 dot 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 n of a k equals 0, which equals the product of p of n of a I equals 0. So log P of n of A equals 0 becomes the sum from I equals 1 to K of log P of n of AI equals 0, which is the sum from I equals 1 to K of F of AI. It follows that minus F mapping from script B of script X to R plus is an additive measure, thus an intensity measure, and the probability that n of A equals 0 is e to the power f of A. Since we are also given in statement 4 that expectation n of A equals lambda of A, and for a process whose void probabilities are e to the power f of A, the marginals would be Poisson with mean minus f of A. So we must have minus f of A equals lambda of A. This means the marginals are Poisson with mean lambda of A, and we have CIP. So by definition, N is a Poisson process with intensity measure lambda. This completes the cycle. Let's consider a corollary for a Poisson process on the half line. A random process N mapping from omega to Z plus raised to R plus indexed by time t in Z plus, though usually R plus for continuous time, is the counting process associated with a one-dimensional Poisson process, S mapping from omega to R plus raised to N, having intensity measure lambda if and only if the following conditions hold. AA, starting with n not equals 0, the process nt takes a non-negative integer value for all t in R plus. B, the increment ns minus nt is surely non-negative for any s greater than or equal to t. C, the increments nt1, nt2 minus nt1 ntn minus ntn minus 1 are independent for any sequence 0 less than t, 1 less than t2 less than tn minus 1 less than tn. D, the increment ns minus nt is distributed as a Poisson random variable with parameter lambda of the half open set Ts for s greater than or equal to t. Furthermore, the Poisson process is homogeneous with intensity lambda if, in addition to conditions A, B, and C, the distribution of the increment nt plus s minus nt depends only on the length of the interval as an element of R plus, but is independent of the starting time t as an element of R plus. In this case, the increments are said to be stationary. For the proof of this corollary, we have already seen that the definition of Poisson processes implies all four conditions A through D. Conditions A and B simply state that n is a simple counting process on the half line. Condition C is precisely the complete independence property of the point process. And condition D provides the Poisson marginals for the increments, which in turn defines the intensity measure. The result then follows from the equivalence 4 in our theorem on equivalences. This concludes our discussion on Poisson point processes and their various characterizations.